Você que está ouvindo esse podcast, o que acha de uma empresa que sempre trabalha para trazer impacto positivo? Assim é o Google. Como? A Duda da Orbi é um exemplo disso. Ela usa a inteligência artificial para ajudar pessoas a recuperarem seus movimentos. É a tecnologia mais útil na vida das pessoas. E tem o Jefferson da Tributei, que usa inteligência artificial para facilitar o dia a dia das empresas. Eles e milhares de empreendedores geraram mais de 188 bilhões com as plataformas do Google. Tem que ser bom para todo mundo.
Precisa ferir a pressão, medir a glicemia ou tomar uma vacina? Na Raia tem exames, testes e calendário vacinal completo. E o que é melhor, tem sempre uma Raia aí perto de você. É fácil, prático e rápido. Dá para ir entre uma música e outra. Procure nossos farmacêuticos. Quanto mais você conhece o que a gente faz na Raia, mais você se cuida.
The Athletic.
F1 is back, and already there's a big tech talking point to delve into with the braking rule change introduced just before the August break. Gary explains what might be going on there, then answers your questions on parc, ferme, rear wings and engine IP. We also hear from battery technology and software specialists about energy in a wide-ranging interview about batteries in motorsport. The Formula One season is about to restart, so what better time for a new episode of the Race F1 Tech Show? The August break has flown by and all eyes will be on Zandvoort for the first race in what should be a technically interesting doubleheader that also includes a visit to Monza. I'm Ed Straw, but the star of the show is Gary Anderson, who I'm delighted to say is with me once again. So Gary, are you ready to get back into the swing of F1 after your own summer shutdown?
Yeah, very, very much ready. I mean, it's obviously... it doesn't seem like a long time, this break, but it does get a bit sort of tedious because you want to see how the season's going to progress. There was lots of action just before the summer break started. Teams catching other teams, Mercedes getting back in the action, McLaren, all of that stuff going on. So to have this break now is a little bit of a sort of damper, I suppose you might call it, in the season. Back in my time, we never had a summer break. You just worked 24 hours a day if you could. But yeah, it's be good to go back and see who's been able to get their head around better solutions for their car and setup wise, because although the summer break's a shutdown, that doesn't stop you thinking about stuff. And that's open for all teams to do a bit of thinking about. You don't always get the time during the season because of the pressure of races coming up to really sort of ratify it all on your own brain really as to what direction you should take. So that'll be interesting. It'll also be interesting to see who comes with what new stuff, because again, at the end of the day, stuff has started to get made by outside manufacturers before the summer break, and it'll be in Zandvoort that we'll see some of it. But obviously Monza then is a completely different circuit, so we'll definitely have to have some updates for there, low downforce updates or low drag updates as such. So these next two races could be interesting to see who's able to carry the momentum on from the early part of the season and who has done the best homework, and then again going to Monza, who's got the best package for there.
Yeah, and I think we can expect to see a decent amount of upgrades for Zandvoort and then the low downforce, low drag stuff for Monza. So yeah, there should be plenty to get into once we start seeing the cars. We've got a fascinating interview coming up on battery technology later in the episode, but let's start off with the usual opening gambit of the Race F1 Tech Show, which is to open the floor to Gary to talk about a topic of his choice. So what's on your mind, Gary?
Well, really, the big topic, I suppose, during this break has been this torque steer or braking systems that potentially has a question mark hanging over it as to whether anybody was attempting to do something or not. So it's just like anything over the summer break. There's not a lot to fill the column inches, so people start writing about it because it's a big thing, and will it scupper teams at the front, or has it been used? Nobody really knows, to be honest. If you read the regulations as they are, I find it pretty hard to not contravene some regulation if you're going to do something to act as a sort of torque steer brake system. Going back to my days with Jordan, we did something like that whenever McLaren brought their fiddle brake out, which is a separate brake pedal and all that stuff to put braking force into the inside rear wheel. That quite nicely. That acted quite nicely as helping to rotate the car, but it also acted quite nicely as to help the traction. So at the end of the day, you can't do that stuff anymore. So you'd have to do it as a hidden venture. We did a system on the early cars in the mid 90s, or I think we started in 1994, because basically the brake pipe length from the master cylinders to the front brakes is quite a lot shorter than the brake pipe length from the master cylinders to the rear brakes. So basically when you come up, you stand on the brakes, all quite happy, the pressure builds up in the front and rear brake system. As the brake balance, you've got it set to that percentage, and that's all okay. But when you come off the brake pedal, the fronts would come off first, and the rears you would get a little bit of locking, because the length of the brake pipe was restricting the flow, which restricts getting the pressure out of the system. So we did a little system where we had basically very similar to a one-way valve, a restricted one-way valve. So you had full flow as far as getting the pressure onto the rear brakes was concerned, or onto the front brakes, sorry, was concerned, but it had a small restriction on the way and getting the fluid back again. And you could change that restrictor to suit so the balance of the front and rear brakes as the brakes came off was pretty equal. And that really is when it's critical for the driver, because that's when you're trying to turn the steering wheel and turn it into the corner. So the last thing you want is one end of the car, hanging onto the brakes. And once you've got the system, then you could play tunes with it, whether you use it or whether you didn't. It was only a matter of changing this little valve and bleeding the brakes. So it worked for us quite well, and we used it for quite a few years. And it actually got more important as the brake lines themselves got smaller diameter, just for stiffness. The restriction became more and more. So the little valve was quite a novel thing to have in there, and it just meant you could balance the front and rear brakes as you were coming off the brake pedal. So that's one of the ways I see you being able to do it, having a restrictor to either the left or right rear brake, so that when you're coming off the brake pedal at the end of the braking, that there's still a little bit of a restriction in one side of the car to help rotate the car. Now, it's not really where you want it. To be honest, you want it as you're mid-corner or just before mid-corner to exit, if you could do it. But that's really difficult to do unless the driver's willing to get back on the brake pedal mid-corner, put brake pressure in there, and then get back off the brake pedal. Now, these drivers do things, and as a two-pedal car, so it's not as though you're doing anything else. You got a left foot to do the braking with. So it is possible to do it. It is possible to come up with a system that would help. Not quite sure how you would do it to suit both left and right-hand corners. I think you'd have to look at a given circuit and see which was the dominant corner where you wanted it to help you, or the dominant number of corners. So if you got 3 right-handers and 1 left-hander that's slow speed that you need some help, then you would do it for that side. But again, the way the regulations read, it says the pressure's got to be equal on the 2 pads clamping the brake disc basically on each corner of the car, and it needs to be equal pressure on each axle. So in theory, that's not what you would have, but you would have equal pressure. It just means that the degradation of that pressure would be different from side to side. So that's a very, very difficult thing to actually measure, and I don't think anybody does measure that. It would be more of a feeling, a driver feeling, and rig testing to try and optimize it. So obviously the regulations now have technical directives being put out, or clarifications being put out about it, and that can happen because, again, the FIA reading through the regulations think, oh, there's a bit of a loophole there, we might close that off. Or another team has said that we've got, can you do this? Is this a solution that's, we could actually incorporate in our car? And the FIA have possibly said no. And then that same team would say, well, we think that XYZ might be using something like that. And it'd all be down to thinking. And again, there's people move from team to team. So there's rumours go from team to team. Rumours are not always actually black and white, but they do go from team to team. So, it's a clarification. It's at a bit of a strange time because normally anything that happens mid-season would be because of a positive identification of a potential contravening the regulation and a clarification of that regulation to try and reduce the risk of that. So it's a bit of a strange time to happen with 10 races to go. So again, let's see what happens in Zandvoort, and then really, where we go from there.
And there's a few things we can gather from the way it's been done insofar as the way the FIA works with the regs. If you do something that they don't want to be legal, but actually with the reading of the rules they won't change it until the next year. They'll say, actually, no, it's a fair cop. We didn't really want you to do that, but the regs say you can. DAS, that Mercedes did, was a good example of that. They didn't really like it, but they thought, well, the regs allow it. So you can't wholesale outlaw something that's not allowed. So this has to be considered more of a clarification of what they think was already in the rules rather than something completely new. It's also worth noting that it actually appeared in the 2026 regs first, and I'll be interested to know the origin of this rule, because it was in the 26 rules that were published in the middle of June. So that was about 6 weeks before it went into the current regs. But of course, the process for getting things into current regs is very different for when you're just doing the first public publication of the regs as the 26 ones were. So we don't know the timeline on that. They could have had it for 26 and thought, oh, that's quite a good idea, let's put it in. I'll quickly read out what the reg says just so that people know what's in. Now, it's an additional sentence. So originally Article 11.1.2, which is Article 11 is all about the braking system. 11.1.2 states, the brake systems must be designed so that within each circuit the forces applied to the brake pads are the same magnitude and act as opposing pairs on a given brake disc. And then there's this additional sentence that's come in that now states, any system or mechanism which can produce systematically or intentionally asymmetric braking torques for a given axle is forbidden. So that's the kind of detail of it for people to get their heads around. It's interesting as well because there's not just the mechanical braking system, is there? You've also got the hybrid element of the MG UK that works on the rear wheels. So there's a whole added layer of complexity, and you can actually say opacity because it's all electronic, and there is obviously the sort of dynamic brake bias and all those kind of things to actually make the harvesting work, and that's impossible to see from the outside and very difficult to understand. So that there's even more means to potentially do things, I guess. And the way I read that reg edition is it basically says the same thing, but it's much more broad, isn't it? In that you couldn't argue, oh, we're doing it that way. It's like anything that creates this asymmetry is illegal. So that feels like quite a sensible additional layer of the reg to me.
Yes, it is. Obviously, if you want to ban or get rid of the potential to do something like that, then it is a more of a black and white set of regulations. The thing is, I don't disagree with you. That probably whenever they sat down and were converting the regulations from 2024 to 2026, and as you say, the hybrid recharge system, the MG UK, basically that's mounted on the engine. So really, it doesn't know about two rear wheels. It only knows about the rear wheels driving through the gearbox and driving the engine. So basically, it's the car speed or the car rear tire grip that is being restricted, and that means it's being restricted by the MG UK. So that's one independent motor being driven by two rear wheels. So it's very difficult to do anything with that because it goes through the differential. You could play with the differential under braking, but it's got so much of the differential setup is involved with the out-and-out handling of the car that just giving yourself something to do some torque steer with the differential and free up one wheel would be nigh on impossible, I think, to get it consistently. So I think it does have to be done with the brakes. And as you say, the force, the way the regulation is written, to me, the max force applied at the brake disc, left and right on a given axle, could be the same. It's just that degradation, how quickly that drops back down again on each side of the car. That would be the thing that would give you a little bit of torque steer and help the car turn into the corner. But again, as I say, it might just be a clarification that's been highlighted as you write the regulations and think, well, there's an opportunity there to do something strange. We have seen, cars with, how would you say, independent rear wheel problems of braking, where the rear corner of the rear brake that caught fire on one side and not on both sides. Which, yes, you can get a visor, cover, whatever you call them, tear off into a brake duct, and one side gets hot, and so on and so forth. For sure, it can all happen. But But maybe it has been highlighted because of the 2 or 3 incidents that we've seen where the rear corners burst into flames. I mean, I think Williams had one a couple of years ago where they burned the whole rear corner of the car completely. So yeah, Red Bull had one earlier in the season where they had a problem with I think it was the right rear. So yes, it has happened. Can happen for many, many reasons, but it might be the thing that sort of, sparked a little bit of a thought pattern in somebody's brain to say, I wonder if that could be happening. But we'll see. Let's see at Zandvoort and Monza if we actually see any big differences, or how the teams unfold and how they talk about it.
Exactly. Well, we'll hear a lot more once in the paddock there. And whenever there's something like this, there's a tendency for the world to interpret it as banning a team from cheating or whatever, but it's never quite that simple. There's always a lot more detail and subtlety going on, and I'm sure we'll talk about that again when we've got a little bit more background in terms of exactly what's happened. Let's get into our tech interview for this episode now. It's all about battery technology, including how it's used in F1 itself, but also in the wider motorsport landscape. You're about to hear from the co-founders of About Energy, which is a fascinating company specialising in battery testing and software. I'm joined by Gavin White, the CEO of About Energy, and Kieran O'Regan, who is the COO. Both are founts of knowledge about battery technology. They'll tell you all about themselves and About Energy in the interview, so let's waste no further time and delve into the world of battery technology. I'm joined by Kieran O'Regan and Gavin White from About Energy, a company which specialises in battery technology, particularly in terms of battery testing and software. Thanks very much for joining us here on the Race F1 Tech Show. Perhaps we could just start off with introducing yourselves and telling us a little bit about the company. So, Gavin, you're the co-founder and CEO of About Energy. So perhaps you could tell us a bit more about yourself and the company.
Yeah, for sure. Thanks very much. Pleasure to be on the podcast, Ed. So my name's Gavin. I'm one of the co-founders and the CEO of About Energy. About Energy is a battery data and modeling company. And we use our specialist IP in battery measurement to make these very advanced simulation twins and collect very accurate data on lots of lithium-ion battery cells. In terms of my background, I did mechanical engineering at Queen's University in Belfast. There I got the chance to do the program called Formula Student, who many people are probably familiar with. So we built this little race car to compete against other universities. And there I got to work on battery packs for the first time and realised just how complex and difficult and challenging battery development is. And that led me to a PhD at Imperial College in London, focused on measuring the thermal properties of batteries. And over the course of that PhD, I realized that measuring battery properties is unbelievably difficult. I ended up inventing a patent to measure a very, very specific property called thermal conductivity of batteries. And then during my PhD, I got introduced through my supervisor to Kieran. And together we've worked for the last just over 3 years now to co-found About Energy. But yeah, over to you, Kieran.
Awesome. Cheers, Gavin, and great to be here, Ed. Quite similarly to Gavin, my background is also doing a PhD, but rather than engineering, that was in chemistry, and I did that at the University of Birmingham. And the focus of that PhD was really just taking batteries we find in household appliances and even electric vehicles and tearing them down to really understand their material composition. And I think as a scientist, that was really interesting to understand how varied the materials that go into these batteries are, and that really impacts the supply chain. Again, like the environmental impact and how we actually get these raw materials from mines into these batteries, and also their performance. So we can talk a lot about some of the differences we see in chemistry and therefore performance between some of the motorsports events we're talking about later. And then my PhD was really focused on how we improve battery performance, again, helping companies reduce like charging times or increase battery lifetime. Again, trying to really understand the material limitations and support companies with their transition. And I think this has been really interesting to sort of follow this in industry in the last few years. And we've seen some quite significant changes in chemistries, and quite interested to talk about that later as well, and how that impacts not just motorsports, but also sort of mass market applications and what we see as consumers in these industries.
Yeah, certainly a hugely fast-moving industry, but quite a baffling one for those on the outside, because I think just about every day you see some kind of story about a leap forward in battery technology, and it's never quite the giant leap forward, but it's always these fascinating incremental things that aggregate into a lot of progress. But perhaps we could start off with where motorsport fits into what you do, because obviously you've got a broad portfolio of clients and industries you're working into, but where does motorsport slot into this for you?
Yeah, so motorsport would be one of the largest sectors for our customers. Motorsports is often very high performance applications, very demanding. And in the world of motorsports, it's important to integrate new technologies as quickly as possible. And often that involves the use of simulation rather than experimental prototyping. You can iterate in a virtual environment much quicker than you can in a real world environment. So using very advanced simulation tools, battery data, battery parameters, is actually a core part of motorsport battery pack development. And actually a significant portion of our customers today actually fit into that category, these high performance motorsport companies that are iterating on that.
And obviously when it comes to motorsports applications for battery technology, the ones that people tend to zero in on are Formula E and Formula One, and there's always a lot of talk about how suitable they are as a testing environment, given that they have to kind of lock in the technology they want ahead of time and for a period of time. So sometimes there's criticism that it's not advanced enough, but as you alluded to there, Gavin, there's that high performance element which I guess plays its own role in terms of trying to drive forward that technology. So where do those categories fit in with development of battery technology?
Yeah, no, I think one of the main things that we find interesting about working with sports is that these companies are trying to push the envelope of technology. And that's not just relevant to the battery, it's relevant to the whole drivetrain. And I think as a material scientist, maybe the assumption was that I didn't realize that Formula One vehicles use batteries. Again, it might be common knowledge for a lot of your listeners, but yeah, all Formula One vehicles have a hybrid powertrain and are really reliant on battery technology. So we found it very interesting to work on not just Formula E tech, but also Formula One tech, because the batteries in Formula One vehicles are so high power because they're really tailored to these region applications. And now we see some of these, and region applications means obviously when you're braking, you want to harvest that energy as quickly as possible and then use that energy to accelerate. And again, that's one of the main benefits of a hybrid powertrain. It really allows these vehicles to have a lot better performance. And yeah, we've been very interested in seeing a lot of these new chemistries end up into more mass market applications. And that really allows us to add a lot of value to our customers and the industries more widely.
And obviously when it comes to battery technology, for a lot of people, batteries are kind of black boxes, aren't they? They're just sort of magical things you plug into things, or they sit in cars or whatever. And one battery looks much the same as another. It's only really size and where they are. But obviously there's an enormous amount going on inside it. So perhaps using F1 as a case study, particularly with the 26 power unit regulations, got a 300 kilowatts hybrid element to the battery, needs to be able to harvest 8.5 megajoules a lap, and in some circumstances even that nudges up to 9 with the way the regulations are. And there's a lot of talk about the challenge of doing that and people pushing back about how difficult it is. So that's quite a good case study for where battery tech is. So why is that such a big challenge? Is it such a big challenge? And I guess in this arena, the key thing is the fact that the regs set the minimum mass at 35 kilos for the actual energy store, the batteries. So I guess that weight side of things is the key.
Yeah, for sure. It's an extremely difficult challenge to design a battery pack for that application. Like, as you say, it's a hybrid application there where you've got both an engine and a battery pack. And my understanding is that the engine's basically going to provide roughly half of the power, and the battery will do the other half. And the engine will basically be running flat out the whole time. So even when the driver's braking, the engine will be running very aggressively to recharge the battery, even though energy's been recovered from braking. So we're going to have battery packs in these Formula One cars that they're going to be being charged and discharged probably 10, 15 times every single lap. And then they're going to go on to do like 50 or so laps. So the actual duty cycle that these batteries are going to go through is going to be extremely aggressive. And the power requirements, so the amount of energy they need to move in a given second, is going to be extremely high. So it's an extremely aggressive application, but I think it's one that suits the kind of Formula One engineering perfectly, like really squeezing the performance. And there's many different areas they can innovate to get that performance. A lot of it's going to be to do with how they extract the heat from the batteries and they keep the batteries at a safe operating window. Another is going to be about how they optimize the battery charging and discharging for lifetime. So put in some clever software to try and manage the peak currents to try and prevent battery degradation. So there's going to be, I think it's a very difficult challenge, but isn't that what Formula One's all about? Very difficult challenge, and then throw the world's best engineers at trying to solve it. But yeah, I think a very exciting project to work on for all them engineers.
Yeah, and I think it's a great point, Gavin, because you touched on sort of the system challenges. I think for a lot of these teams, there's also like the cell level challenges. It's like, can they find cells with the right power and energy requirements with the new Formula One regs? Like I've been surprised, like tearing apart these different batteries. They can be so different in design and chemistry. And like, as you said, Ed, like even these batteries, they look seemingly the same on the surface, but within them, they're very different. So again, that's sort of a key topic we help not just Formula One and Formula E with, but it's like the battery cell selection topic. Again, there's so many different batteries and they all have similar formats. They could be cylindrical cells, pouch cells, and they might have different chemistries within them, and like it can be very difficult to understand like which one is the best for a certain application. So that's where data and simulation can be very useful. But you can start to virtually design a vehicle with a battery and really understand how to sort of optimize its performance for a use case.
And Gavin, you mentioned the challenge of making all the fine measurements in order to create the simulations. So let's say you've got a Formula One battery pack or a cell performance, you're trying to understand it. Can you give kind of an idea of the range of parameters you'd need to measure in order to create an accurate simulation? I imagine there's some obvious ones, but there's probably countless ones that only a specialist would ever even get close to thinking of.
It does. It gets very niche very quick. You're right, Ed. But yeah, some of the high level ones would obviously be things like the battery capacity, so how much energy it stores, the battery resistance. These things sound very simple, right? But actually, even the energy a battery stores is very, very difficult to measure because it depends on so many factors, such as like the temperature, the discharge rate, the state of health of the battery, and even things like the battery resistance. Battery resistance is a function of temperature, state of charge, and current history. So it's like more of a resistance map is the way you need to think about batteries. But then going into more nuanced parameters, so you've got the thermal properties, so thermal conductivity and heat capacity, and they basically determine how hot the battery gets at its core inside and how quickly it heats up. And then going over to electrochemical parameters, maybe Kieran, you can talk a little bit about the electrochemical parameters.
Yeah, good point, Gavin. So yeah, that was really the focus of my PhD, Ed, where it was about not understanding sort of the cell level properties and how these cells would form a pack, but dismantling them and actually measuring the internal components within them. So we measure sort of the electrodes. Again, like a battery is not homogeneous mass. It has many different components within it. It's got like a negative electrode, which is typically graphite and contains silicon, and the positive electrode contains a lot of these sort of raw materials and critical minerals we hear a lot about, like cobalt, nickel, manganese. And then there's also liquid in there to sort of facilitate ion transfer. So again, it's a very complex device and component. And what we do is really dismantle these batteries and measure those individual components. Again, some of the material properties like the electrode thickness, as I said, and even doing microscope imaging to understand their particles and the performance of these particles. Again, this allows us to build up a very complex model which we can deliver to customers, and they can then sort of model the physical states within these batteries and then really sort of push the boundaries of regeneration or fast charging, or even understand at a more physical level how these batteries degrade and how to mitigate that. It is a very laborious process, but very valuable because a lot of customers in automotive and motorsports don't necessarily have these sort of material catered facilities. So that's why they come to us to really support on those topics.
And when we're talking about Formula One batteries in particular, they're obviously lithium-ion batteries, which, from my understanding, is a fairly mature technology and that there's been a lot invested in that. Is it fair to say that's probably the most advanced area of battery development? And if so, how much more is there to get out of a lithium-ion battery? Are you kind of getting into the point where it's very, very small returns that are being found in it, or is there still a lot more to go?
Yeah, I would say it's still, well, I guess we have to say this because we're in the industry and we're trying to sort of push the envelope of technology. But I'd say it's definitely not the most mature battery technology. Like if you think about mass market automotive, like lead acid is extremely mature, like the whole performance and recyclability. And there's not much more we can sort of enhance the performance on that chemistry. But lithium ion batteries, they have still quite a significant way to go in terms of reaching some of the theoretical considerations of how we think about power and energy. And we're seeing some, I guess, technologies in the lab and being announced by companies which do represent a step change in maybe lifetime or energy or power. But as you said earlier, like these breakthrough sort of announcements, they do take many years to come to fruition. And I think we're still maybe many years off seeing a real step change in mass market technology. And some of the chemistries that your readers would maybe have or listeners would have heard of before, which are coming to the market, which aren't mass market yet, would be like solid state batteries. Again, that fits under the umbrella of lithium ion technology, but just has like a different design using like a solid material to move ions rather than liquids. And then that gives like better energy lifetime and potentially cost. But again, like these batteries have been developed for 10 to 15 years, maybe even longer in research labs, but still a huge challenge to produce them, mass manufacture them and commercialize them.
Yeah, and I just wanted to add as well that when it comes to battery technology, there's kind of two main areas for like development. There's the actual battery science development where we're developing new materials that really push the performance and energy envelopes. But then there's also the kind of the technology being commercialized and being able to produce batteries at very, very low cost at very high scale. So obviously, eventually, the very cutting edge materials work its way down into being able to be manufactured at scale. But there are kind of two different areas of battery development. So when we look at like mass market automotive, they're very much using the latest technologies that can be built at scale affordably. But when we go down into high performance sectors, especially areas like Formula One, they're potentially working on materials that haven't yet being manufactured at scale economically. These are like extremely high performance materials that are somewhat built by hand. Like there's going to be a lot of manual steps in them processes. So when we look at Formula One battery technology, it's maybe a few years ahead of what you might see in an automotive car because it's literally straight out of an R&D lab from a cell manufacturer as opposed to coming off the end of a high volume production line.
That's an interesting point because there's sometimes criticisms that the regulations don't allow technology that's so far forward. But I guess that maybe is in the sweet spot where it's enough ahead to be pushing the technology, but without being so far ahead that it's just a flight of fancy and completely disconnected from the level of understanding that exists today.
Yeah, exactly. I think it's perfect in that respect. It's always been a criticism of Formula One that it's got so high performance that it's actually not relevant to real applications anymore. But I think in the world of batteries, from what we've seen and heard, I think there's very exciting developments that really push the performance envelope of the materials that could work its way back down into consumer applications. So yeah, quite strangely, some of the same batteries that are used in consumer products would be used in applications like Formula E, for example. The batteries are almost identical. And in Formula One, they're much higher power, which would suit sort of different applications. But I think there is a tangible link between the two.
Yeah, and typically when new batteries come to market, what they can't compete on is like cost and volume, because it takes a while to like fully scale them. But they do have better performance. So sometimes niche industries like motorsports are a great way for new batteries to break into market before they can sort of achieve those economies of scale, which make them competitive for consumer electronics or automotive.
I wanted to ask you also about the solid state batteries. Obviously, you mentioned that earlier, and solid state batteries are one of the things that you do read constant stories about. Major breakthroughs for it. It's one of those technologies that feels like it's going to be everywhere tomorrow, and it will be everywhere in the future probably, but it's maybe a bit further off than just around the corner. But perhaps you could explain the difference between solid state batteries and what we see now with, say, a lithium ion battery in an F1 car, and also the potential for solid state batteries in the future in terms of what they could offer in performance in terms of energy density, specific energy, that kind of thing.
Yeah, happy to sort of talk through the differences. So as mentioned earlier, like our traditional batteries, They have two electrodes. So one's like a graphite material, and then one's that transition metal material, like the negative and positive electrodes. And then the key thing is those two electrodes need to be electrically insulated. So in conventional batteries, you have this very thin plastic separator, and that thin plastic separator needs to allow ion transfer. But plastic isn't great for that purpose. So you have this liquid electrolyte. And this liquid electrolyte is often flammable. Again, when you think of batteries going to thermal runaway, a lot of that's caused by that flammable liquid we have in these batteries. So again, there's a big safety concern with including that component in these batteries. So companies are trying to sort of get rid of that component and sort of move to a fully solid battery. But one of the issues with doing that is you obviously have now a solid rather than liquid trying to facilitate that ion flow, and traditionally solids are a lot worse for that purpose. So again, like the power and energy traditionally has been quite difficult to reach parity with traditional technology, and that's really what a lot of the development work has been trying to achieve. But if these batteries can be commercialized, you obviously get a better safety because you're not using that flammable component, but also the energy density can be better because you have a lot more efficiency when you're trying to actually design it, and you can build batteries that are very compact because that sort of ceramic solid can be made to be very thin. So again, it really facilitates better performance, but also better safety. And I think one interesting thing is I've been tracking sort of solid state batteries for probably the best part of a decade as a material scientist. And I think, as you said before, like they've always been maybe 6 months, 1 year for like mass market commercialization and never really come to fruition. But I think an interesting thing is sort of tracking the companies in this space. And one interesting, I guess, thing on our side is that we've now started testing solid state batteries in our lab. Again, like these Chinese manufacturers, which maybe aren't known by many people in sort of in the West, are now mass producing these solid state batteries, and they are now appearing in sort of mass market vehicles. So we recently purchased from China like a solid state battery, which is maybe about 1.5 meters sort of in length, like a 100 amp hour battery. So 20 times the size of one you might find in like a Hoover or some consumer electronics device. And these are really interesting because they are now commercial, but still have a long way to go to sort of reach the parity in terms of cost and volumes we spoke about earlier with traditional technologies.
Well, I guess something that if you could make that sort of technology down the line work in a racing car, that's a good way to drive development because of the size challenges and the mass challenges and all those sorts of things, and also I guess the safety testing that you get from the slightly more extreme environment.
Yeah, I think how these technologies are then implemented in Formula One is going to be very, very interesting. The rules and regulations are quite wide open, so it's going to give a lot of flexibility to the Formula One teams about what technology they pick. So whether it's lithium ion and what flavor of lithium ion, whether it's NMC, LFP, silicon anodes, semi-solid state, or whether they make the full leap to full solid state immediately or in the near future or the long term. I think that's going to be very interesting to see how it plays out. But one of the problems of this is it's going to be very difficult to know what the teams are actually using. So although there's going to be a lot of this innovation, it's kind of going to happen behind or inside this closed box. But hopefully we should hear some very exciting announcements and partnerships between manufacturers and the Formula One teams to do with that technology supply. So I think the question is still very much open on that one as to what they end up picking.
It's an interesting point you make there about actually how much of the knowledge falls out into the rest of the world, if you like, because obviously everybody wants to keep the technology proprietary, but if you want to advance the breed, you do need to be making that information public. You need to be publishing papers on it to really try and drive the breed. So is that an area where motorsport maybe needs to buy into trying to feed the wider world, not just if you're a manufacturer driving your own technology, but accepting there's a kind of common good there that needs to be contributed to? And would that have a greater accelerating effect, do you think?
Yeah, I think there will be some mechanism for people to find out. Like, one good thing is there's so many Formula One fans that are so dedicated, so many sleuths out there that will be able to track down who's making the partnerships with who, like who's connected with who on LinkedIn, etc. So I think we will get a pretty good sense over time of what's going on. But yeah, hopefully it's something that can be shared at a high level and not too much of it is hidden. I think it'd be a real shame for like all of us fans to not know exactly what technology is being employed and how it's being employed. Because one day we all want to see that technology filter its way down into the applications that we use ourselves, right? Whether it's phones or cars or laptops. So it'll be interesting to see, what technology partnerships are signed and how then technologies are then brought to the market.
And looking perhaps on the horizon in terms of this sort of technology, obviously materials wise, again, if you read news stories about batteries, there's often all sorts of outlandish stories about this material, this unlikely material. Pretty much every day there's something, and I'm pretty much every kind of material has been attached to being the future of batteries. So what is the potential there? What is the reality of how other materials can be brought into it? Because obviously there's only so much you can mine of everything you need to go into batteries. So as batteries and electrification become ever more wide, this is going to need to happen, isn't it? There's going to need to be other types, and also different types better refined for specific applications. So it's a very broad question, but so what's the sort of long-term future of battery technology? What are the most interesting avenues?
No, I think it's a very good question, Ad, and I think sort of two very different answers compared depending on what industry you're thinking of. I think for motorsports, especially Formula One, I think we're going to see more of the same but better. Like I think it's going to be very difficult for motorsports companies to sort of transition from the traditional chemistries you see today, which Gavin mentioned, like NMC, these nickel-based chemistries, and LFP, iron-based chemistries. Again, that there's still a lot of performance that can be enhanced and developed just by making these batteries bigger and like changing the internal design, maybe increasing certain chemicals within them, like silicon. Again, that has a big impact on performance. But then in the wider market, we're seeing a lot of very exotic flavors of chemistries, as we spoke about, like solid state, sodium ion, even like LFMP, so adding manganese to those iron-based chemistries. I think it does take a long time for those to reach the sort of performance parity with traditional batteries. So like they're going to find niches which won't necessarily be motorsports, which could be like grid storage or e-mobility or consumer electronics. But I think for the next few years, we're really going to see, in my opinion, more of the same in Formula One and even Formula E, and new battery chemistries will find their niches elsewhere.
Well, we've gone sort of to the broader horizon on that, so it'd be good to kind of step back to what you're actually doing. So let's say a Formula One power unit manufacturer comes to you and says, right, we want your help with battery development, with simulations. How do you actually go about the process of building up that sort of 3D view of the how things are actually working? I mean, you talked about sort of tearing apart batteries, that kind of thing, literally doing that. But how complex a task is that? What would you actually do? I guess you'd need the hardware first and foremost to experiment with.
Yeah, exactly. For us, as I said earlier, our core IP is battery measurement. So it doesn't matter what battery technology that is, whether that's lithium ion or sodium ion or NMC or LFP, doesn't matter. So we have our own test lab in central London where we would receive the batteries. So a customer would typically send us some samples, maybe 4 to 10 individual battery cells. And then we would run them through a suite of testing and characterization. And that can take anywhere from 4 weeks up to 12 weeks, depending on the sort of measurements we need to take. And when I say we measure these battery properties, I think it paints this like quite rosy picture that we take the battery, we plug it into a machine, and then out come all the measurements. Whereas in reality, I think what you described them earlier as, Ed, was a black box. And in a lot of respects, a battery is a black box where you plug it into a machine and you get out all these squiggly voltage traces. And then you have to use your expertise, your knowledge to infer what must be going on inside. So Kieran talked earlier about measuring electrode properties. One of the properties we measure would be the diffusion of lithium through these materials. That's not something you can measure directly. You have to take observations of lots of other things and then infer what's going on inside. So when a customer sends us a battery, that's what we do. We bring it to our lab, we run all these experiments, and then we have this modeling activity where we have to infer what is going on inside that battery. And then we take all of that knowledge and expertise and we turn them into these battery parameters that then get fed into like a simulation twin of the battery. And we typically deliver them simulation twins in a very common engineering software, and especially motorsport, is MATLAB Simulink. So we can build this like simulation tool in that platform. And we purposely stop there. We stop at the cell tools to allow other people to take them tools and build their own designs and build their own IP. So that's one of our kind of core principles as a company is we want to enable engineers. We want to give engineers the tools, the data, so that they can go and develop a system using our expertise in like measuring these different properties and parameters of batteries.
Yeah, and I think you touched on a good topic there where we help customers, Gavin, which is obviously battery pack design, but those models can be used for also battery pack cell selection. Again, when it comes to starting a battery pack program, as we discussed, there's a myriad of cells. So these models can be used very efficiently for that cell selection topic. And then once they've selected the cell, they can then use those models and that data to really try and assemble these batteries virtually into the optimal configuration to work out like how big the pack should be. And then once you've sort of designed the basic architecture, you can use these data sets and models to really optimize the configuration. Again, work out what temperature your thermal management system should be, like the state of charge window of the cells. Again, trying to understand how you maximize regen. Again, simulation can be used for really all those topics, and it allows customers and companies to do it virtually rather than physically, which is obviously very laborious and resource intensive. And obviously very time consuming. So simulation allows them to really accelerate their development on those topics.
I'm thinking about those kind of simulations. Obviously, there's the kind of the normal function kind of simulations. But when you're talking about, say, a Formula One car, when you're trying to optimize how it works around a lap, and for example, your optimal harvesting and discharge strategy, and also how hard you can push the battery in terms of the duty. I guess that's the other element. There's the extraction once you've got the hardware developed element as well. So that's as soon as you talk about simulation, that's where I start thinking about with motorsport, because that's the kind of final end product area where they do it. So I guess that's also something you could get involved with in terms of pushing that technology to the limit, how much you can ask of it without it risking failure.
Yeah, exactly. So what's standard practice in the automotive industry now is model-based design. So you would develop a design just using models. But what's very much standard now in high-performance sectors like Formula One is a model-based control and predictive control. So a technology I learned about a few years ago, which I just thought was so extreme and incredibly clever in Formula One, is that as the car will be going around the track, they'll log its location on GPS. And then the turbo would be programmed using GPS so that as it comes into a corner, the turbo starts spinning up so that when the driver needs the power exiting the corner, the turbo is already spooled up and you have that high power. So this is using like a model predictive controller to basically say that, well, I'm approaching the corner at say 150 mile an hour. In 0.3 seconds, I need my turbo to be spun up so I can harness that power on the exit. And I think when it comes to batteries, it's going to be the same and more. It's like this model predictive controller. So going into a corner, you know that you can potentially regenerate, I don't know, a certain amount of energy given your speed, your cornering direction. So can the battery handle that? How is that energy dissipated? So it just gets more and more advanced kind of simulation being used to optimize every single aspect of the vehicle's performance around the track. And how they do that, I think it's going to be incredibly exciting, and hopefully them learnings can feed their way down into other industries.
Yeah, certainly it's going to be very interesting come 2026 to see how similar the different manufacturers are in terms of their output. Obviously, we've covered quite a lot of topics there, but obviously not being anything approaching a battery specialist myself, I'm aware of my own limitations in asking questions. Is there anything we've not touched on that is important in this area that people should know about? There might not be anything, but I always like to ask that sort of thing because I'm very aware I can overlook vast areas of importance.
I think maybe talking about Formula E and in the comparison to Formula One could be quite interesting, especially, which is interesting that like Formula One companies have the ability to choose their own battery cell and engineer their own system. But for Formula E, it's very different where every company uses the same battery cell and battery system. So I think that we possibly see that maybe change in the next few years where as the sport develops and becomes more mature, these companies will be giving a bit more autonomy. Again, like motorsports has been great for big companies developing and improving technology. And I think that would be amazing to see for batteries, but that hasn't been the case today. So I think, yeah, that we could maybe talk about Formula E. I don't know, Gavin, do you have any points to add on that?
Yeah, I think it's a really good topic. I think on the face of it, you would assume that the applications are very similar, right? There are both batteries that go into these kind of formula style race cars, but actually the technology is completely different. One's like an energy application. So in Formula E, you start off with 100% state of charge, and you have to make that energy last the whole race. There's no opportunity to significantly recharge. Like, you can obviously do small amounts of recharging when you brake, but not significantly. Whereas in Formula One, you can actually top that battery back up to 100% on every lap, where you can use the engine to recharge the battery. And then that breeds two very different kind of streams of battery technology. One is energy based and one is power based. So power being the amount of energy you can extract in a given second, and energy being the total amount of energy that's stored. So I think it's good to have these two streams, because they both push forward the technology in them two different areas of application. Like, an automotive car is obviously much closer to the energy based, where you have a certain amount of energy you need to make last 500, 600 miles. But if you take things like your electric vacuum cleaner, they're power based. They only need to last like 10 minutes, but they need to push out huge amounts of energy in that short burst. So I think having the two categories is, and just for people's context to know that they are very different kind of flavors of battery technology, but they both push forward very, very significant areas that are required for our consumer use of battery technology.
No, it's an interesting point, because I guess Formula E offers a very different balance in terms of how much of your mass budget and your space budget, if you like, you can spend on the battery side of things as well.
Yeah, exactly. And that's a real challenge in Formula E, is to design your battery pack to fit geometrically, like the packaging into your car, but then also to have the energy to last a whole race. And then there's a lot of optimization can be done to get the efficiency out of that battery, so that you can potentially use a smaller battery more efficiently or a larger battery less efficiently. So it gives more control to the software engineers, and how that's deployed through a given race is exactly like when that energy is used and when it's saved.
Yeah, so it makes it a vastly different energy challenge, I guess, than Formula One. And obviously, there's a lot of other areas of motorsport where we're seeing some battery technology coming in, all electric and hybrid as well. So I guess this should only grow over time as electrification in the road car sector gradually builds. That's going to become the norm rather than the exception in terms of motorsport use, and that will, I guess, throw up a lot of different areas of development that haven't necessarily even been thought of as yet.
Yeah, definitely. I think it's really sort of a good showcase for us going to Goodwood recently. So we went to Goodwood of Festival Speed and got to see a lot of the sort of motorsports and hypercar applications. And it's been very interesting, obviously, to see how chassis design and engines have changed over the last few decades, but batteries as well. Again, a lot of these hypercars like Pagani, Bugatti, they all have batteries. So again, we're going to see batteries continually becoming a big part of hypercars and motorsports. And yeah, I think it's just very interesting to sort of see those technologies on showcase.
And of course, you're involved with McMurtry as well. I should have mentioned, because that's another interesting, very much a unique project going on there. So what are you doing with McMurtry?
Yes, that's super exciting. It's one of our few customers we can talk about publicly where we signed a technical partnership with McMurtry Automotive. So McMurtry, they make one of the world's fastest electric vehicles. It set the hill climb record at Goodwood, I think smashing the record by 2 seconds. And it's a battery powered car, and it uses this fan beneath the car to help suck it to the road. And what McMurtry are doing now is moving to the next vehicle, the next design. And they need tools and data to help them actually design the battery pack to meet the lifetime warranty obligations, but also to meet the performance and kind of the thermal management. So we provide that data for McMurtry. They use a manufacturer called Molicel, and we test them batteries. We collect very, very accurate data, develop these simulation tools, and then McMurtry are able to use them tools to help them design that battery pack in the best way possible. So yeah, it's a super exciting application, an incredible car. We seen it go around Goodwood, and it was the only car that everybody applauded and took their phones out to see. It was unbelievably rapid, and it's great that our technology is going to be in the future generations of that.
Yeah, it's fantastic when you've got a car that's just very different as well as very quick as well. So that inevitably catches the eye. So yeah, hopefully we'll see some interesting things coming up with that partnership. Well, thanks very much, Kieran and Gavin, for your insight. If anybody wants to find out a little bit more about energy, you can look them up online. It's about Energy, I think, is the proper name. A fascinating company. And thanks very much for giving us some insight into what you do and also the general state of battery technology.
Awesome. Well, thank you, Ed. It's been great being on the podcast, and yeah, great questions.
Yeah, a pleasure, Ed. Thanks very much.
Let's get on to our listener questions now, always a favourite part of the podcast. If you've got a question you'd like to ask Gary about F1 technology, ancient or modern, something to do with his career technically, as long as it's vaguely connected to tech, you are on safe ground. You can send that to podcasts@therace.com. That's podcasts@the-race.com. You can either send it as a written question, an email, or even record a voice note and attach that to the email. Remember to let us know who you are if you send a voice note so we can hear your question. You've got 3 questions today, Gary. The first one comes from David Salyer, who says, when Honda comes back to F1 in 2026, will they be able to use any existing technology or IP they had in the engines they supplied to Red Bull, or do Red Bull own the IP to these engines, and will therefore Honda almost need to start from scratch?
Well, the regulations have changed a little bit, David, for 2026 anyway. So I'm not saying Honda need to start from scratch. The way I look at it is, why do teams poach other people from other teams? And that's to try to learn something from what they were doing. The IP is safe unless you arrive there with your with a drawing and say, here you go, this is the magic gizmo that you need in your car to make it work. So as long as you arrive there with something in your brain, then fine. You can't unlearn something that you've learned. So what Honda have done through the years has been quite incredible, really. And in the latter years, it's been partly with the Red Bull technology group. So I'm sure Honda will be looking at starting again, because once you print something, once you do it and it's on the car or in the engine, you'll have a better idea. It's always like that. The minute you press print on the old manufacture this component, you think, if I put a little bit bigger radius on there, or a sharper corner on there, or done that, I could have made it lighter, I could have made it stiffer, I could have made it whatever. So you'll always have a better idea tomorrow than you had today. And you've got to live with that sometimes. So I think Honda, their knowledge will go with them. The actual black and white sort of IP, no. I think Red Bull do own that now. But it's what is IP really. It's if there is a certain gizmo in there that's a really good piece of kit that nobody else has, and Honda blatantly reproduced it for 2026, then Red Bull might have a little bit of a question mark over it as to how they gone about doing that. But I'm sure that, as I say, new ideas will come along and it will all filter out. And I'm looking forward to it, because it puts another PU manufacturer in the system, which is obviously, if we do lose Renault, then I think it's good that another one's coming in.
And it's worth just clarifying, because there's a lot of people who get confused about the Red Bull Honda deal as it is. Although they're Red Bull powertrains engines, as they're labelled, they are entirely Honda engines. Honda owns all the IP, and they will also have been very careful to firewall things off, as it were, so that Red Bull won't have been able to just dismantle a Honda engine and have a look at it and use it for their own design, because that would be a breach of IP. However, having familiarity working with the engine in terms of what Red Bull are doing will be useful knowledge for them. But anything Honda does with Red Bull, they can carry over if it's relevant to 26, whether that's specific parts or more likely just knowledge and methodologies and that kind of thing.
Well, yes, and it's two-way. Obviously, there's a new regulation, as I say, for 2026. Red Bull will be trying to optimise that new regulation around their knowledge base, and Honda will be trying to optimise that regulation around their knowledge base. So the two could diverge, or as we see with car design, which is the thing we see, the cars diverge to begin with in a set of regulations, and then they all come together after 3 or 4 years. So it's the way things happen, unfortunately. But there is 2 manufacturers that are going to build the new hybrid unit, and I'm sure there will be knowledge from one to the other that'll be the same, and I'm sure there'll be knowledge that will be different. So again, I'm excited about it because I'd like to see what Red Bull can do as an independent, and I use this word loosely, drinks company, manufacturing a power unit.
Yeah, very much so. They've done everything right in terms of recruitment, the spending on facilities, etc. But making a whole new powertrains company coalesce and produce something that's market leading is a huge challenge, but if anyone can do it, Red Bull can. Let's move on to our second question now from Paul Hodgin, who says, I was wondering how a team adjusts their rear wing. At the Belgian Grand Prix, I saw completely different wing levels in the Red Bull. How does an F1 team trim their wings? Is it done by a specialist machine, or do they have a few different ones they can use? Thanks again for all your great work.
Well, Paul, overall, obviously if we just take Monaco to Monza, there would be completely different rear wing assemblies, completely different beam wing assembly, and probably some modifications to the diffuser, all to try to reduce the drag of the car and keep as much downforce as possible. But then whenever you go to the higher wing levels, you end up with this little box that you're allowed to put things into, and for Monaco, you have the maximum you can put in those two boxes, the beam wing box and the rear wing box. But whenever you see things like the Belgian Grand Prix where you're never quite sure because the first part of the track and the third part of the track is all about straight line speed and the middle part of the track is all about corner speed. You want downforce in that middle part of the track, but you want less drag in the up straights. You sort of get that compromise. Now, I'm never a great believer in trimming the trailing edge of the rear wing to get you to a downforce level, because with anything, the trailing edge... The trailing edge, you put the rear wing at its maximum because that gives you the maximum height for the best efficiency as far as the sort of frontal view is concerned, and it gives you the maximum leverage because of the trailing edge being as far back as possible. And when you start cutting that trailing edge and reducing it, it's let's say it's a cheap way of getting lesser rear downforce, which will be lesser drag. But it's not the most efficient way. The most efficient way is still to keep that trailing edge as high up and as far back as possible and as uniform as possible. But sometimes you have to make these compromises, and especially now with the budget control, maybe that rear wing, the difference in a rear wing that would have been the same level as the wings we saw on the Red Bull that had a trimmed rear flap, the difference might have been, a thousandths of a second per lap on simulation. So sometimes you make those compromises just to because you have it, and it saves your budget cap. So you need to sort of balance it. But normally you have a range of wings. Each team will probably have at least 5 different levels of rear downforce, rear wing. Then you've got gurney flaps you can put on it, bigger or smaller to a certain size. And then from there on in you can take each of those wings and you can trim them a bit if you want to. So, you probably end up with, 10, 12 solutions of levels of rear downforce that go up a slope, basically. If you put it on a graph paper, it would go up a slope as far as downforce is concerned relative to drag. And the nearer you can get that slope to be a sort of linear, I suppose you might call it, or at least a consistent slope, then that's the package that you use, and then you pick the downforce and drag level for a given circuit. So they're all very variable, but each team, as I say, will have, as far as the main structure is concerned, probably 5 different rear wings minimum.
And it's also quite a live battleground, isn't it? Because Red Bull's setting the standards in terms of aero efficiency. So others are kind of battling away, trying to build up to that. And we're seeing a lot of different versions, not just of rear wings, but the beam wings as well that they use in combination for that sort of system. So there's still actually quite a lot going on there in terms of teams optimising what you'd call their sort of family of rear wing options.
Yeah, I mean, go back in time a little bit whenever we sort of found out that the Red Bull was very quick in the straight when it was using DRS. I sort of come up with a theory that it was a triple DRS. Whenever they opened the rear wing up, it affected the beam wing performance, which affected the diffuser performance. Now, the diffuser performance is much, much better than the rear wing or the beam wing. So the last thing you might do is have too much effect on the diffuser, but still it's all a drag reduction. So if it all happens when you don't want downforce, then it doesn't really matter. The rear top wing on an average sort of normal circuit would be efficiency of 3 to 1. the beam wing would probably be very similar, or even maybe a little bit worse. But the fact in combination with the diffuser, which is probably at 10 to 1, something like that ratio of drag to downforce, all of that works together as one. So other teams have cottoned on to that. However, I still think that the DRS being used in qualifying is a bit of a grey area in my book, because it's supposed to be an overtaking tool, and the last thing you do is follow another car in qualifying to overtake it. So why use it in qualifying? And if you didn't have to use it in qualifying, or if you weren't allowed to use it in qualifying, then it would bring a whole different package of downforce levels for the rear of the car, because obviously qualifying and the race are two things that you've got to be good at both, really, to be honest. And if you can get rid of a draggy rear downforce package in qualifying because you can open the DRS, then it means that you benefit from something that you really shouldn't be having to use. And it's the same for everybody, so it's all right. But I would love to see a race where, for qualifying, no DRS is not available, and then you can use it in the race for overtaking, which is what it's designed for.
Well, at least we've only got another season and a half of DRS in its current form before we move on to the new rules. Different things going on there with active aero, but not the DRS as we know it. The final question is from Sam Quint, who says, I have a question on Parc Ferme as it relates to teams being unable to make changes to car setups between qualifying and the race. I know at some point I understood why this rule is in place, but at this point I can't remember why that is. Everyone wants to see teams at their best. So why is it that the current Parc Ferme rules handicap teams from ever being truly at their best? If they pursue a setup for qualifying, they compromise their race seeding and vice versa. I want to see every team put their best foot forward for the event at hand in all cases.
Yeah, Sam, so do I. I think what you say there is 100% true. Now, going back to your first point there, I can't remember why that is. It was really done initially because people were changing so much stuff on their car because, lightweight radiator exhaust systems, so on and so forth, just to optimize the car a little bit for qualifying. So they could put more ballast underneath the car and make the car faster in qualifying. And then they put on the race durable bits and pieces, down to even upright assemblies, and suspension was getting changed. So it was done to initially stop all that and reduce the cost of basically going to a race meeting with two cars as such, a lightweight car for qualifying and a normal car for the race. Now, when I say lightweight, I mean you can't run under the weight limit, as George Russell found out at the last race of the season, or the first of the season. But still, you would put lightweight componentry on the car, and then put ballast underneath the car, which lowers the centre of gravity and in theory makes the car go faster. So it was done for that reason many, many, many years ago, and really it's outrun itself, I suppose you might call it. So I think that it is time, and I hope for at least 2026 they would review it, because obviously with Parc Ferme rules, you're not allowed to change any components on the car, but because of that, you're not allowed to really touch the car, which is wrong. I would try to put together a system where basically let's say the pit lane opens 10 minutes earlier than it does now before a race. I don't know what it is exactly, but the pit lane's open for 20 minutes, I think it is. Let's say you opened it for half an hour. And during that half hour, the team is allowed to adjust, and adjust is a loose word here, to adjust the car setup. It's not allowed to change any parts unless you've got written permission from the FIA before that happens. So if something's cracked or whatever and you need to change it, fine. Get a permission from the FIA that it's the same component, and you can do that prior to this. But come the pit lane opening for the race, you have the opportunity to raise the ride height, change the brake cooling, change the engine cooling, whatever you want to do. And each team should have a declaration form to say what they're doing. So whenever we see the last minute thing when the tyres come up on the screen, or the commentators seem to know about the tyres, at that point in time, that declaration would be available to them as well. So they could turn and say, well, Ferrari have raised the ride height, front ride height, or they've adjusted the rear dampers, or they've done whatever, So that's just adjustments. You can't change something. You can't put something different on the car. It's the same dampers, the same springs, the same torsion bars, the same everything. But you can adjust them. So it's up to the team then to, design their car with a mechanism that allows you to adjust stuff as quickly as possible. because you've only got that 10 minutes plus your reconnaissance lap. So there is a solution to the things. There is an opportunity to make the cars better for the race. For example, let's say it rains, there's a downpour before the race starts. That would give you that opportunity to raise the ride heights, get it out of the water a bit, and stop the potential aquaplaning. Or, just the simple stuff, take some camber off, or whatever you need to do for a wet setup. But it's not only just for the wet, it's for different conditions. Obviously, tyre durability, tyre degradation. There's a different setup from getting the tyres to work well on one lap to getting them to work well for 20 or 25 laps. So at the end of the day, I want to see the same as you're saying, Sam. I want to see the cars, their neck being wrung for qualifying, get a lap time out of them, and then in the race, it's a bit more about the strategy of the whole race meeting, how the driver drives with the car. So I would welcome a change in that regulation that would allow the teams to have that little bit of a fiddle, as I say, not change componentry, but actually adjust whatever the car has got on it.
Yeah, and there is a halfway house, isn't there, that can be achieved, as you've explained, between not allowing anything and avoiding the situation where cars are being rebuilt overnight. And obviously there's a lot of effort being put in to make sure staff aren't too overworked with 24 races and making sure you have curfews and that kind of thing. So it's perfectly doable.
That's really why I'm saying just to extend the time for the pit lanes open, because at the end of the day then it's a last minute thing. So, other teams can't say, oh, Ferrari have changed the front ride height, perhaps we should do the same. You have to think on your feet yourself, and your declaration sheet would be filled out before your declaration sheet would become like a worksheet for the mechanics. So you do your declaration sheet saying raise the front ride height by a millimetre, put another degree of angle on the rear wing, or whatever it be, and that's your declaration sheet, and that's the work list for the mechanics. So at the end of the day, it's too late in the day for other teams to react to it, but it's late enough in the day for you to optimise it. And I think that we, Joe Public, which I classify myself as now, would like to know what level the teams go to for those changes, and that's why I say a declaration sheet to say, soft tyres, blah blah blah, all these bits and pieces. This is what we've done for the race, and that all comes out, as the cars head off on their warm-up lap, let's say.
No, a very sensible solution. And as I say, if you'd like to hear some more of Gary's sensible solutions to real-world F1 tech problems, or just simple explainers, there's no question too simple or too complicated, Gary will give it a go. Send that to podcasts@therace.com. That's podcasts@the-race.com. We're obviously going to be turning our attention now to Zandvoort. We're going to be back after the Italian Grand Prix, so join us then for more from Gary.
The Athletic.